Thank you, Thomas. Welcome everyone to this webinar. I will share my screen to show you the agenda of today in presentation mode. Well, this is the life cycle assessment. This webinar is the principal value of the LCA in the circular economy and its influence in the battery industry. Today, we will integrate the principles of the life cycle assessment, LCA, and circular economy in order to help redefine the future of the electric vehicle batteries. We will start with our experts in regarding the life cycle assessment circular economy for optimal management of electric vehicle in order to give more sustainable circular transition and electromobility. Then in the segment of the navigating the sustainability landscape of the battery pack through LCA, we will highlight the importance of the eco-design and sustainable practices from the beginning to the end of the battery life cycle. Then myself, I will explain you the overview of the strategies to minimize the environmental impact through the new recyclability treatments to integrate them in battery LCA models. Um, in the section of the power up recycling LCA and its impacts in the battery industry. And finally, and lastly, we will examine the life cycle analysis of the advanced lightweight battery systems for electric vehicles, focus on mainly in the innovations aligned with the European battery waste regulations and contribute to resource efficiencies. And after the speakers give out their speech, we will have a section for the question and answer. As Thomas comment before, using the post for the question, please put the name for the speaker that your question is going, and we will have the panel discussion in which we will put common points between the different projects and lessons learned in this webinar today, and we will solve the questions and answers, and finally to do the wrap up of this webinar. So the first speaker will start with Aitor Picatoste for the Project Liberty to give their his speech. Aitor is here for.
I'll just take control of the screen. I think you guys should be seeing my screen now. I'm trying to go in presentation mode as well. Okay. So hello everyone. This is Aitor from the Liberty Project, and I'm going to be talking about the LCA and circular economy analysis for electric vehicle batteries with a small twist on how regulation affects the LCA and vice versa, how the LCA and circular economy can affect regulation. So first thing first, who am I? So I'm, as I said, Aitor. I'm writing a PhD thesis on the circular economy and LCA of batteries for electric vehicles, which is very adequate for the topic. And I am part of the Circular Economy and Industrial Sustainability Group at Mondragon Universitatia, where we look at the eco-design and also life cycle management of different industrial products, in this case, electric vehicle batteries, but also renewable energy sources, any industrial product. And just to come and contextualize a bit the topic, we just received a new regulation for electric vehicle batteries or batteries in general. So the regulation for the batteries and waste batteries of the European Union was accepted in July this year, and it came active in August. This includes a lot of different batteries, but especially electric vehicle batteries. So the official definition is there, but in general, just providing electric power for traction of hybrid or electric vehicles. It's what defines an electric vehicle battery. And again, I must say that this complete regulation for the European Union includes different batteries, so industrial batteries, LMT, but it has a urgency, so to say, in looking at electric vehicle batteries. So the timeline here, down here, you can see how the delegated act, especially for electric vehicle batteries, is coming first compared to the rest of the batteries. So now, how this affects the Liberty Project, which is the reason why I'm here speaking in behalf of Liberty within Colabat, right? So the Liberty Project, it's a European innovation project, which is aiming to design an innovative electric vehicle battery with 5 main objectives, which would be improving the autonomy of the vehicle, improving the total mileage of the vehicle, improving the safety of the vehicle, also improving the charging time, so reducing the charging time, and which is our part from Mondragon, and especially my part, it's to improving the sustainability of the battery. So just going and measuring that the battery, the new battery, is less, at least 20% less impactful than the benchmark battery. So here you can see what the motivation is to look at also the regulation, because it comes hand to hand with what we're trying to measure here, and also what we're trying to develop in Liberty. What we've done to accompany the Liberty project in what the technological improvements, or how the technological improvements can come into play for this impact reduction. In Mondragon, we did a parallel analysis with nickel cobalt manganese batteries, so the same chemistry that we will be using in Liberty, just to understand especially how the life cycle management of the battery can improve or can impact the sustainability of a battery, and how realistic it is to gain some benefits here. So just as an overall description of the study we've done, and then I'll come into understanding how the regulation comes and helps this or not. We propose just a standard electric vehicle battery coming into a vehicle and lasting 10 years of first life, without considering any early failures or nothing like that. And then we proposed 3 different scenarios just to understand how this second life might come into place. So the first scenario would be just taking the battery out of the vehicle and recycling it, either through pyrometallurgy recycling or hydrometallurgy recycling. Again, just aiming to understand how the recycling process also can impact the sustainability of the battery. Then the second life would be, or the first option for the second life would be going into another second life electric vehicle. That would be another extra 6 years added to the battery life, and then again going and recycling it. And finally, the third route for the life cycle management would be a repurposing of the battery in a standalone house for another extra 10 years. So pretty much we're gaining longevity with minimum changes to the battery, just some adaptations, and just trying to understand what are the benefits related to having a standardized second life for a battery. So I'm going to go a bit fast comparing the batteries we're using. So as we're part of the Liberty project, again, we went to the state-of-the-art battery. This is not specifically the battery we're using in Liberty as a benchmark, but pretty much a battery that it would be a standard of the industry. And we compared it to the Liberty battery in all these 3 scenarios, just to understand how much the Liberty battery would be improving the sustainability. This next, I'm going to go a bit fast here because I don't have so much time, but again, the reuse scenario, we're adding 6 years to the lifetime of the battery in a second life. In the repurposing scenario, we're adding, as a standalone house with photovoltaic energy, we're adding another 10 years to the life of the battery. So the longevity aspect is coming into play here. And for the recycling scenario, which would be the last choice, so in the pyrometallurgy scenario, yeah, we're getting a bit less recovered material, and the energy consumption is slightly higher or a lot higher in this case compared to the hydrometallurgy, but also it's a bit easier. So we're also considering these two routes, so to say. Finally, what are we analyzing, or what are the metrics we're using? We used global warming potential as the standard measurement for the impact of any product on any industrial product, and also because it's the metric that the regulation is pushing for in terms of measuring the impact of the battery. So that's one thing. And on the other hand, just again trying to come back again to the relationship between the raw materials, the circularity, and also what the regulation is pushing for. We went to and calculate the abiotic depletion potential of minerals, focused on, again, critical materials coming into the battery. Apart from this LCA analysis, we performed a circularity analysis using the product circularity indicator, which is quite a complete indicator, including raw materials, also the efficiency of manufacturing, taking into account any extra materials that we're using, and of course the circularity of the loop, so the recycling aspect. We wanted to understand how the different metrics affect each of the scenarios we proposed, and being able to convey these results within the project properly. So I'm going to just jump ahead and show which was the result of this, and then I'm trying to convey how the regulation affects this thing. So here you can see 6 different scenarios. So each one of the 3 second life scenarios, so no second life, the reuse scenario, and the recursive scenario, then they had a twofold way to be recycled, so pyrometallurgically and hydrometallurgically. And here, mainly the idea to convey is that for the LCA categories, so LCA impact categories, so in orange you've got the global warming potential, and in green you've got the abiotic depletion potential. You can see how the second life, so any longevity activity, greatly improves the impact. So this is all savings. So the assumption we made gave the result, or yielded the result, that we can go up to 60% of mineral impact savings with a proper second life management of a battery. However, and this is quite shocking, the circularity metric, so specifically not the LCA, but the circularity metric, doesn't show this improvement as much. So this comes to discuss.
Sorry,
Yep.
sorry, Aitor, you have 1 minute, please.
Okay, I'm going to be very fast then. So
Okay.
what I'm trying to say is the savings are big for longevity. The circularity doesn't convey that much. Again, we did a different study with other circularity metrics, and again, we see that there are some misalignments here. And finally, yeah, with somehow how to come to this with the regulation. We identified with this study that maybe the regulation doesn't provide enough context to help out in solving these issues we identified. I'm going to just go to the last one. Okay, this is a quite dense slide, but what I presented here are different measures on different regulatory obligations that come into play, that most of them tend to be looking at the circularity. So having recycled content minimums, having also minimum minimum quantities to be recycled, and then we've seen that these are important factors, obviously, but the longevity aspect is way more important, and it's not being looked at so deeply, or at least the regulation it's not so clear. So we're looking at further delegated acts to act on this, and having like some minimum longevity definitions and quantities that could help build this bridge between what we know from LCA and what we can be doing in terms of regulation, and how regulation can guide this transition to a more sustainable EV battery. And yeah, this is all. Sorry for rushing at the end, but yeah, this is the time we've got.
Thank you, Aitor. Yeah, the questions we will address later. So it is now we move to Violeta to show your topic, please. Is your turn, your floor.
Okay, perfect. I think you can see my screen now, right?
Yeah.
Perfect. So, my name is Violeta Vargas, and I work at EURECAT as an advanced researcher on life cycle assessment and, well, sustainability impact methodologies. And I'm going to present to you a bit of what we're doing in MARBELL project, the part of LCA, of course. So first, a little bit of context. I think you already know, but still, I think it makes sense to remind a little bit of facts on this. We are all aiming to reduce greenhouse gas emissions in this world because we don't want to burn in it. So we are trying to do this, and mainly we are trying to reduce emissions coming from transport, because we know they make a big impact within the distribution of greenhouse gas emissions in the world. So in this process, we are focusing on electrification of vehicles to make it more sustainable, or with less CO2 emissions during their lifetime. In this goal, we also see that the battery pack has a great significance in the electric vehicle. It has a very high weight. It's between, I don't know, half a ton and almost a ton. And the weight distribution tells us also how we can improve this weight within the electric vehicle. So more or less, it's 60 to 75% coming from the cells and materials that make the battery, the efficiency directly related to the battery. And then 25 to 40% is coming from the metal casing, the cables, the thermal and battery management system that also provide part of the efficiency of the battery. So there's a lot of room for improvement over here. So in MARBELL project, we have different goals. We have the goal of reducing the weight to 20% or more. The charging time will be reduced to 25% and 25% less. And we are also aiming to reduce the life cycle assessment impact in a 40%. To do this, we can see that, as we saw before, part of this is coming from the battery pack distribution, like the casing, right? So to assess this, how do we improve this? How do we measure this? Is through design. We have to design a new battery that can include improvement in these areas. To do this, we started with a methodology developed by EURECAT that is very easy to apply, and it has 4 steps that are easy to follow. First, we identify some hotspots that allows us to focus on the problems that really have an impact on the battery pack. Then we develop a set of strategies. We readapt or adapt these strategies to technical and technological requirements. And then we define specific actions that we can follow through the life cycle assessment, or the life cycle of the battery, including the second life and the end of life at the end of the second life. So a little bit of this methodology, a little bit of explanation would be the first step to identify this hotspot during the life cycle stages, the different life cycle stages of the battery. We used a benchmark analysis. We did a preliminary assessment, an LCA well, a life cycle assessment and a life cycle costing assessment to really identify these hotspots and where we have to focus on reducing or improving the environmental and cost impact. And once we did this, we came up with this little like sheet that have a lot of information. It tells us the impact range that this hotspot may have in the different life cycle stages of the battery. And we describe all these hotspots in detail. Then after this, we follow to the second step, which is create a repository of strategies in a datasheet format that we can identify where is actually this strategy going to affect the most. We can see here a bit of example on this different strategies, like lightweighting, for example. It would have a high impact on the first life cycle stage, would be the raw material extraction and component manufacturing. It would also have a high impact on the use stage of the vehicle because the reduction of the energy consumed during lifetime. Then a medium impact on the second life due to the same. And then a very low, more low impact on the end of life of these materials from the battery pack. We did this for different strategies, and then we followed to the step number 3, which is adapt this set of strategies to the technical and technological requirements. We did a workshop with all the parties, with all the members of MARBELL from different levels, management, designers, everybody who could participate in this workshop was giving their own opinion, and we aligned the strategies and we came up with 10 full strategies at the end for eco design. These are like more, not general, I wouldn't say general strategies because they're applied to MARBELL specifically, but they're still not specific actions. So we had to go to the specific action definition. For this, we also followed what all the people from MARBELL had to say, and we came up with a set of actions that are being and going to be applied through the project, all through the project. Within this actions, we can see them here, the 14, but I won't be going into detail of any of these ones. I'm just going to mention a few. Like the first action would be to use recycle and recyclable materials, for example, for the extrusion of aluminum profiles, or introducing a weldless connection to the cells to support disassembly, repairing, maintenance, and all this. But how do we measure this? Again, we go back to life cycle assessment. We need life cycle assessment to actually calculate the environmental impacts, and also life cycle costing to calculate the cost impact of the different designs. We already did a benchmark, we did a preliminary assessment, and we have the results from the first assessment. And now we have to, and we have been doing it during the MARBELL project. We've been studying different materials, different options of design to see what the impact will be and how is this going to improve the battery pack from MARBELL. For this, applying the life cycle assessment methodology, we needed to define a functional unit in some life cycle stages of the battery. As I said before, the life cycle stages would go from cradle to grave, and it would include the raw material extraction and components manufacturing, the use of the battery in a vehicle, then a second life of this battery in different options, and then the end of life of the batteries in different options as well. For this, we defined 2 different functional units because, as you may know, in life cycle assessment, we have to define this functional unit that is going to be the base of all calculations, and is based on the function of the product that you're studying. In this case, it's a battery pack. And if we consider this battery pack installed in a vehicle, the function of the vehicle per se is to move from one point to another. So it would make sense to evaluate this, this product in their function or their final function, which is moving from one point to another and measuring it as 1 kilometer. So all resources will be calculated for the moving of this vehicle during or through 1 kilometer. But also it makes sense to consider the battery as the provider of energy. And then aside from the vehicle, because we need this to include the second life also of the battery. So the other functional unit would be 1 kWh as the energy provided by the battery itself. We are doing these two functional units within the study, and this will help us, or has been helping us, to quantitatively assess, as I said, the hotspots and all the processes that are really affecting the product, which is the battery pack in this case. It has been helping us to identify and prioritize different elements that had the most impact. We did this for different materials and design, as I was saying before, and this will help us to develop impact reduction plans and to really achieve the goals of the MARBELL project of reducing the impact in 40% on life cycle assessment. And this will also help us to communicate the results in a standardized way, following the life cycle assessment methodology. So the conclusions for this study for the application of eco-design and life cycle assessment together is that combining these two, or putting life cycle assessment within the eco-design, will help us really identify the key environmental concerns and also the cost concerns that are related to material selection, weight consideration, the vehicle lifespan. It's all included in this study. And also we have learned that a collaborative eco-design approach would lead to more sustainable, efficient, and cost-effective solution, because we have to include all the team and all their opinions to really achieve better, applicable, efficient eco-design actions. And this is the end of my presentation. If you have any comments or questions, I'll be happy to address them at the end, as Victor was saying before.
Thank you, Violeta, for your presentation. Well, I will give my presentation. I will share my screen. Okay, can you see it?
Yes.
Okay. My presentation is about the power of recycling in LCA and impacts on the industrial battery. Yes, I can start that this problematic that we have, because we know that the demand of the lithium batteries is projected to grow over 30% annually, reaching the market size to 2030. So this is important to increase the prevalence of the electrical vehicles in order to have more sustainable the life cycle management of the batteries. So there is different points or topics which are addressing this is challenges. As you can see in this slide, we are the industry and the academy and research project are addressing the battery technology, charging infrastructure, the cost reduction, supply chain. But in this webinar, I will focus on the handset recycling and second life, for the sustainable and efficiency of recycling processes and reports for these batteries. But more, I will focus on the recycling aspects. This is important to mention that the recycling is the one key element of the circular economy, because the recycling allow us to have more reducing of the reliance on raw material extraction and decrease the environmental footprint. However, there is a lot challenges to address the safety and efficient recycling of a growing number of the electrical vehicles. So uh, uh, here, one of the points more important to achieve this is how is the role of the life cycle assessment in order to identify this is impact in the recycling processes, because the life cycle assessment can give us the opportunities to improve the recycling processes and the technologies using the information from the current recycling rates, and they are challenges in terms of the economical perspective. The life cycle assessment can give us the battery design recycling, for example, modularity, circularity, etc. And we can close the loop, and in order to provide advisements for the role of the policies and incentives for driving. In HELIOS, in the project that I am involved, uh, it's a high performance modular battery pack for sustainability urban electromobility services. We are addressing several objectives in this project: hybridization and combination, combining the high energy and high power cells, the modularity aspect and the scalability design, advanced BMS, digital twin, and ultra fast. But we are focused in the work package 8 of the activities related to the life cycle assessment and sustainability. In the end of life, we are developing a new innovative procedure for robotic material disassembly. We are exploring the performance and second line applications, and integrating the life cycle assessment in the recyclability aspects as well. And in Helios, we are exploring the recyclability analysis for the metal recovery, specifically for two chemistries: the nickel metal cobalt and lithium titanium oxide component. All this is analysis can provide out the LCA, the full LCA calculations in line with the new batteries regulations and digital battery passport. Uh, Regarding the processes that we are exploring in Helios, we are exploring the flotations and the hydrometallurgical recycling for the nickel metal cobalt composition with graphite and lithium titanium oxide mixture. We are exploring different routes in order to have the more optimal procedure for this recycling. And basically, the flotation is a physical mechanism in order to separate the graphite from the mixture of the chemistry. Now in Helios, we are exploring the different experiments in order to have the good recovery of this graphite. Approximately 55% of the graphite is successfully recovered with a grade of the 98%. But we are exploring more optimization of these processes in order to achieve the higher purity. On the other hand, we are integrating the hydrometallurgical process in order to separate or recover different metals like magnesium, manganese, lithium, nickel, and cobalt. And I show you in this slide the life cycle model principles applied to these hydrometallurgical processes. The functional unit here is 1 kilogram of the recycled black mass, and through the specific software we have to construct the life cycle inventory for the different materials in order to have this purity in the end of the mass obtaining these processes. We can explore different environmental impact indicators, as you can see in this table, but I will focus on the global warming potential and the biotic depletion elements. And regarding the first results, we have that the global warming potential is around 3.66 kilograms of the CO2 equivalents, to in the associated to these processes, which is more contributed to the sodium hydroxide and nickel sulfate and other components which can contribute in these CO2 emissions. And other impact categories were explored, as you can see in this table. But my message here is to say that it is a leader part of the life cycle assessment of the end of life in order to fit the full cradle to grave LCA calculation that we will do in the project in order to have the whole environmental perspective of the from the cradle to grave um, scope. So in addition, we will do the consideration, we will take into account the consideration of the credits of the recycling of these materials in the life cycle assessment model. For that, we will do the circular footprint formula, which is provided for the European footprint method, in order to have more consistent of the life cycle analysis in this battery developed in HELIOS project. Also, we will integrate, or we will pay attention the new regulation of the batteries in order to not only to focus on the recycling, on the content of the materials at the beginning of the processes, but also for the different aspects, for example, for the digital battery passport and the second life recycling information, etc. Yeah, this is are the main remarks that we have in HELIOS. The first one is that the anode graphite can make up 14 to 22% of the weight of the lithium battery. So this fourth flotation can be potential to be used for the recycling in an anodic material. The HELIOS, the hydrometallurgical solution process, can provide us recovery, a good recovery percentage of the lithium, manganese, and nickel and cobalt, ranging in 98% to 99%. And finally, in the life cycle management of the HELIOS, we will support the inclusion of the sustainability and circularity related to the information between the new regulation, because it is important to take this is aspects in line with this new regulation with the recycling processes, uh, uh, and in addition to have the track for the inventory and data for the digital battery passport. So this is all from my side, and yeah, we can explore the questions later. Uh, yeah, I think the turn is for Hye
Yeah.
Chowdhury
Yes.
for the ALBATROSS project.
Yeah. Can you see my screen?
Yeah.
Okay. It's Hye Chowdhury from Technomotive Solutions. The title of the topic is about the LC analysis of advanced lightweight battery system for electric vehicle. And this work is actually generated from the ALBATROSS project. If I move on to the next slide. Right, okay. This seems to be working. Okay. So are you in the first slide still? Just give me you can share again, not in this mode. Sorry about that interruption. I think yeah, you can see my screen. If I move, yeah, that's fine. So this is the second about that's why I'm saying this work is actually generated from the Albatross project work actually. So this is Albatross project title is about the
Sorry, hi, we don't see your
yeah.
screen.
yeah, you have done seen this screen. So I'm in the third slide. Is that okay?
No, we don't see
Yeah.
the slide.
If you
Oh,
want, I can
uh,
share if you have.
okay, no problem. Just a minute, 1 minute. I can
Okay.
share it again. I understand. Just yeah, few minutes. I shared the screen. Now it's okay, I think.
Yeah,
Can you see my screen? Yeah.
but you have to put in
Yeah,
the
presentation
full
slide.
screen.
Yeah, it takes time. So if I move, yeah, now it's moving. Last time it's not moving. So this is the second slide, which is about what I'm saying just already. The work is generated from the Albatross project, so which is about advanced lightweight battery systems optimized for fast charging, safety, and second life applications. And so these are the objectives of the Albatross projects. You know that already we have some other projects also working on these objectives. One is about the weight reductions, another is the charging time reduction, another is the increase the driving range from 300 kilometer to about 500 kilometer, and also we are increasing the peak energy density. So these are the mainly objective of this one. Actually, all first three objectives, so four objectives. So what I understand that will actually reduce the environmental impact. That of what I'm showing later. So that's the scenario. What we are doing actually, we will we are working on the cradle to cave life cycle assessment of the Albatross battery system. So this is the assembly. So first we are working on the cradle to gate. I mean the construction phase of the battery pack assembly. So how we generate the battery. So this is the design, and then we can focus on the use phase and then focus on the second life. The end of life. So that's why what we call the cradle to grave life cycle assessment study for the Albertus battery systems. So this is our what we have done so far, but we are continuing to be working on the cradle to gate LCA for the Albertus battery system. So this is what we have planned. So there are four sub-assemblies, the battery cell, battery management systems, battery enclosure, and thermal management systems. We divided, and we are continuously inventorying the data from these four that four subsystems. I can say that. And then what we have done some inventory for the LCA battery cell, battery enclosure, and some inventory for the battery management systems from the partners, and from the Albertus projects. So our database, we are using EcoInvent database and other database, industry data and other database we are using. And also what is our intention to be showing the results in terms of what functional unit. So that's why we are planning to be do maybe 1 kilowatt hour of energy delivered or 1 kilometer traveled, or maybe initially we have done also 1 kilowatt hour of battery capacity. So that's why I'm just showing the results for these three in terms of a three functional unit later. So we are using CIMA Pro LCA tool to evaluate the environmental impact using impact assessment methodology, Impact World Plus midpoint version 1.03. So this is actually the framework to evaluate the environmental impact of the cradle to gate LC of a Albatross battery system. And the construction phase of the Albatross battery systems. There are four modules. That four sub modules create one module, and there are 92 cells in a one sub module. And this is actually we framework what we have generated in CIMA Pro LCA tool in that four that assemblies, battery cell, battery enclosure, and thermal management systems, and battery management systems. And we invented all the data from the partners and converting all the resource consumption data in terms of a functional unit. I would say that this is our 1 kilowatt hour energy delivered, or energy capacity of the battery, or 1 kilometer of traveled. So this is our assembly in the SIMA Pro. And this is the results what we have using the, the impact assessment methodology WAL Impact 2002 WAL plus midpoint. So this is where we are applying to, translate the inventory data into the corresponding environmental impacts. So here I am showing only the carbon footprint of the ALBATROSS battery system, comprising, the three sub-assemblies: battery cell, battery enclosure, and battery management systems. And you can see that about 72% will generate the environmental impact from the battery cell, say about maybe 12% from the battery enclosure, and 5% from the battery management cell. So this is, so if I compare my results with the current state of art, what they have got, so I can show you in the bottom of the line, the carbon intensity, I mean the carbon footprint per kilowatt hour of electric battery capacity. This is actually result for the 1 kilowatt hour of electric battery capacity. So what we got about 60 kilograms CO2 equivalent, but the range from the literature studies we have found from the 30 to 400 kilograms CO2 equivalent per kilowatt hour. The different literatures from this literature, we're just comparing our results. Okay, it is fine so far. And this is actually the comparisons between the one sub-assembly to another sub-assembly, what percentage of the one assembly contributing to in 18 different metrics, that environmental metrics. So we are more or less much interested in the climate change in the long term and the short term, in the global temperature potential and also in the global warming potential. This is a impact assessment methodology showing these categories, and also other categories you can show. Or so that representing contribution of the 18 environmental metrics in different sub-assemblies. And this is the results for 1 kilowatt hour of energy delivered, which is we have found about 64 gram CO2 equivalent per kilowatt hour of energy delivered. This is our results saying we considering our battery capacity is 75 kilowatt hour, and considering the charging time, that 1000 times cycle, 1000 cycles, and considering this one, we estimated the total energy delivered by the battery, and that's why we have found this one. And we're converting all our resource consumption data in terms of a 1 kilowatt hour of energy delivered. This is and this is our current state of art, what we found, which is about 10 times larger than what we have found here, right, from the literature. 2017, quite literature, I hope. And then finally, I'm also demonstrating the results in terms of a kilometer traveled. So what we have found from here, we see that this is actually about 16 grams CO2 equivalent per kilometer of car, medium-sized car travel. This is what we have just calculated here, which is considering 300,000 kilometer travel, the battery lifetime. This is what we have considered here, and then we comparing our results with the current state of art, which is about 9.5 to 60 grams CO2 equivalent from the secondary sources, what we found from this recent literature. This is our so far for the ALBATROSS deliverable. I mean the task what we are working on, cradle to grave LCA of ALBATROSS battery systems. We are inventing the data continuously for the other sub-assemblies, I mean the thermal management systems, and also for the use phase and also for the end of life phase. Then we compile all this data for the three phases: construction phase, that end of life phase, and then also use phase, and what we call it is a cradle to grave LCA. And we can comparing our results with our state of art results. This is our intention, and this is all about from my side, I think. Thank you very much. If you have any questions, then we can discuss. Thank you.
Thank you, Okay, maybe we can give the audience to maybe more or less 1 minute
Yeah.
for more questions, and then we can start with these answers and the
Okay.
panel of the discussions.
Okay. That's fine. Okay.
Thank you.
Thank you very much.
Hi, hello. Just a reminder to the audience. So any specific questions to one of the speakers, you can address in the Q&A window, please now. So far, we don't have any question. Otherwise, then Victor, we can move first to the panel and then maybe have some wrap-up questions later on.
Yes, we have a question from, let me see, from Thomas Montes. Do you consider Second Life for the life cycle assessment? I think this question, well, in the context of the HELIOS project, could be answered, but I think it's more properly in the first for the liberty. Maybe Aitor, you can say something about this, or yes, in all
Yeah.
projects.
Just shortly, what I presented was the comparison of not having a second life compared to two second life scenarios. So, in for Liberty case, that has been considered. It's only a root of the project. So the project is going to develop the complete battery and have the door open for a second life. But in the calculations, we've included second life. Yeah.
Yeah, I don't know, Violeta, if you want to
Yeah,
give.
we're
Yeah,
also considering Second Life for at LCA as the life cycle assessment in MARBELL, and also for life cycle costing as well.
yeah,
We still haven't defined the scenarios for Second Life yet because we haven't reached that part of the project, but we will consider it.
yeah. Uh, from Elio's project, it is the same, because you know that the second life is the for the objective of this perspective is to extend the life of the battery. It will be included between the use phase and the recycling at the end of life. So in the life cycle assessment, we will include this repurposing of the batteries in the model. Yeah, I think this question is is addresses. I have a question, for example, from Aitor. I think it's very important for the environmental impact categories to reflect the the um, the the sorry. I, I, okay. Uh, why do circular economy indicators is not included in the impact categories? What do you think about it? Is this important to include the circular economy indicators in the life cycle assessment impact categories as well?
So yeah, thank you for the question. What the circular economy indicators we believe they are trying to do is to push the, let's say, circular economy mindset within designers and industrial designers or engineers or producers, whatever. And we see that the European Union it's believing in circular economy to improve the sustainability of the batteries, right? So we've got the European Green Deal coming in, and we've got the circular economy actions in general. And we've also seen how this new regulation, it's coming also very focused on the materials, also the Critical Raw Material Act. So all this, it's related to circularity. And at the same time, we believe this axioma of that which is measured can be managed. If you are not able to measure the circularity, you're not going to be able to be managing this. So what we understood from the beginning, and also again when we performed this combined LCA and circularity analysis, we've seen that you can have different information inputs to improve the sustainability of the battery. However, also we've seen that maybe the metrics that now are extended for circularity, they're not properly adjusted for the needs of the actual electric vehicle batteries. So maybe they're not considering longevity enough. Maybe the recycling is accounted in another way. So yes, circularity metrics are important, and we believe that it's important to come in the battery industry with circularity mindset. However, the LCA is a very robust way to have data and to properly understand where the hotspots are coming from. So a combination of both and doing it properly, it's very necessary, I would say. And that's what I try to convey, that circularity metrics may be not properly adjusted to electric vehicle batteries.
Yeah, thank you. I fully agree with you, because actually we could include the in the life cycle assessment models the circular aspects and recycling, and it's very robust from the life cycle assessment. We know that itself the life cycle assessment is very complex when we are including these aspects in the model, in particular the second life, because we have a problem with the functional unit for the second life, because the applications of the battery in the second life is not necessary to be applied in the again in electrical vehicle, can be applying a stationary energy source. So it's very complex, but we can complement this circular economy indicators with another approaches. For example, the LM MacArthur for the circular economy has a model to calculate the circular economy metric or indicator. But again, it is another history and very complex as well. But as you said, we can complement both approaches. Yeah, thank you.
Yes, I would like to just comment that
Yeah.
it is important to include like both aspects sometimes, because some of the circular economy strategies are like more directed to the development of new technologies. Like lab level technologies are not really fully understood with the life cycle assessment results, because we have higher environmental impact from recycling, for example, and different technologies, different levels of technology that can only be seen as a positive aspect if we evaluate the circular economy approach. So yeah, it's
Yeah,
very interesting.
that is
Yeah.
right. That's a right. Good point. Actually, taking advantage that you are explaining this, I have a question that it is related your speech. Is how do you ensure that the eco design and LCA methodology uh, to be are not static but involved with the advancements in the technology and change the sustainability goals? Because it's a kind of the photo, but what happened with the emerging technologies? What do you
Yeah.
think?
Well, I think life cycle assessment, it says it on its own. It's an iterative process, right? So
Yeah.
if we include life cycle assessment during the eco design as well, and we go working from the beginning of the project or the beginning of the development or the design of anything, then we can go iterating the results and applying different technologies, different aspects, different materials, trying new stuff. So it is true that life cycle assessment at the end, the result is a picture of a moment. But if you continue applying eco design and life cycle assessment during the development, then you'll get this, it'll still be pictures, of course, but you can be updating the data that you're including in your assessment. So,
Yeah,
I
that's
think that's
right.
the way. The iterative process or the iterative characteristics of the LCA included in eco design.
Yeah, that is right, because as you mentioned, actually the ISO 40044 explain that this is an iterative processes. And the other thing is, in this is project which are in the early stage, people sometimes thinks, but why we have to apply the life cycle assessment if this process is not in the commercial or massive scale? Okay, that is right, because it is linked to the data that we have to do in the life cycle assessment. But we can use the data that we have at lab scale, pilot scale, in order to provide the early environmental performance of this is new technology. And this is the point. The life cycle assessment is flexibility for us, because this characteristic to be iterating, we can refine the life cycle assessment model when we have the robust data and commercial scale. That is right.
Also, sometimes it's forgotten that we are not only including the technology part from the producing
Yeah,
aspects, we're also
yeah,
including all the life cycle stages, and this can have a greater impact during the use stage, for example. Even if at the beginning, if it's a lab scale technology, then you will have a higher impact there, but you can also understand that it's coming from a lab level technology.
yeah,
Then you apply this solution to the use stage and you see the benefits of applying this, and then it makes all the sense to
yeah.
do life cycle assessment, including all the life cycle stages, of course.
Perfect. Yeah. The I don't know if anyone from this the panel want to add something of this, but I have another question. Oh, let me see. I have a question here from the Daniel Cruz. From what you have learned from previous study, what proportion of improvement in terms of the percentage should we expect to rather to create impacts on batteries in the future, either by kilowatt hours or by kilometers?
Yeah. Okay. Maybe I can take this one. I
Yeah,
don't know if it's yeah. So what I've shown, it's kind of an estimation, but it's been properly analyzed. So it's also coming from real industrial data in a sense. So we're looking at maybe 15 to 20% of impact reduction in the two categories I chosen. So global warming potential and adiabatic depletion potential of minerals. So in general, depending on the LCA impact categories you chosen, you might have a bit different. But I'm going to say that just applying the new technological developments we are seeing right now, already the impact reduction is going to be around 20%. If we go and apply some other circularity aspects, we are really recycle all the critical materials as the regulations come into play. I think this can go up very soon, up to 30%, something like that. I would say maybe it's not a safe bet, but it's a realistic goal, going up to 30% in impact reduction.
Yeah, I fully agree. And it is depends in which life cycle stage we are focused as well, because yeah, for example, according to my experience in the batteries, the manufacturing and the production stage has a higher environmental impact, not only in carbon footprint, actually in all, in most of the impact categories. If we focus on this life cycle stage, mainly the chemistries of the batteries, the processes for the production and manufacturing, because there is a lot energy spent in this stage, we can address this percentage that Aitor say us. Yeah.
Yeah, just to add and a bit better response to the question, yes, I am considering it per kilometer or per kilowatt hour delivered. So just
Yeah.
to the side note. So our calculations, the numbers I presented are by kilowatt hour delivered, as used in function.
Yeah.
From the
Actually, okay. Go ahead, Violeta.
Yeah, from the benchmark assessment that we developed in MARBELL, we also found more or less the same results, but it's different for the different life cycle stages, and it's basically like the greater change is this in the use stage. If you consider the reduction on weight and the energy consumption during all the life cycle stage, also making it like a longer life cycle, well, a longer life for the battery. So yeah, and more or less we found that during the use stage it would be an improvement of 50%, 80% even. So from literature, of course, and then we'll prove it at the end with the results from MARBELL. But yeah, let's hope we stay within that range.
Mhm. But I think from my expertise, I think this question is always difficult to answer, because we have a lot of environmental impacts. Each environmental impact category has different units, different dimensions. It is very difficult put together in one score, single score, and if we compare with the baseline, to say, well, the reduction was X%. It's very difficult to answer this question, because we have to consider the functional unit, the environmental impact category, etc. But we try to do this. I have another question which is very interesting, is about the scarcity and critical raw material, because we know that the battery, there is material, for example, the cobalt, it's a critical raw material, and we have the other aspects for other metals, which is scarcity. But actually, this is a particular question from my side to my colleagues, because so far I didn't find any indicator which include the critical aspects. We have the abiotic depletion for the similar methods, but from my point of view, the critical raw material is not included in the model, and we have other methods for the surplus or category. It's included the scarcity, but not the critical. The critics. What do you think? How we can address this?
Well, yeah, it is complex. From life cycle assessment perspective, at least, and current methodologies for characterization of impacts is not included. But there are methodologies that include this criticality index Actually, at EURECAD, we developed one of this index methodology for criticality, but this is another aspect. I mean, it's not included in the life cycle assessment. It's more like an inventory assessment and then a criticality index developed after this inventory of materials. So it is a different approach completely, but it is including like, I don't know, it's different like the circular economy aspects. Well, this would be another one to include in our studies. So we have to combine different things in our study. Yeah, I guess.
Yeah, so similar to what Violeta said, I don't see the criticality factor coming in play in life cycle assessment. But again, maybe coming back to what I said regarding the circular economy indicators. So we've been looking for different indicators, and we identified an indicator calling to this consideration of criticality. And yeah, if I'm not mistaken, because it's this top of my head, of course, it's called Global Resources Indicator, and it has, I think, three different aspects. One of them would be just the capability of recycling the material you're looking at, but also the scarcity of the material in general for in the surface of the earth, and also I am, yeah, don't quote me on this, but the geopolitical availability, I think it's another factor to take in account. So how the relations are within the countries that are extracting and you as a person who are consuming this resource. So this again comes into play to define, or the need to define what metrics we're looking at, because I think everyone, but Victor, in this case, you're identifying a need for criticality. Violeta, you guys solved it internally, so to say, in EURECAD. You identified something like that. We've also looked at it, so I guess, yeah. And then again, I don't want to be coming into regulation, but if we are aiming to find standard numbers and uh, being able to provide a 20% big number, whatever, we need to have an established, first maybe scientific consensus, and then also some kind of established foundation for us to be able to provide this number.
Yeah, absolutely. I think from the methodological point of view, it's challenging to include these concerns about the criticality. But so far, for the audience and for us, we have this abiotic depletion indicator, which consider only the consumption of the minerals on the surface of the earth, and we have the other method or indicator with its surplus or potential, which consider both of them, scarcity and the consumption of the minerals in the surface of the earth. But I expect it's good to know that from EURECAD is exploring of this own methodologies to include this criticality in these aspects. Uh, Other question what is very important is regarding to the functional unit, the because the functional unit is very important in order to reflect the results and the inventory or data for the inventory. What do you think? What is the better option to include this functional unit? Kilowatt hours storage or capacity in the battery, or for example kilowatt hours but consider the efficiency of the battery with this delivery. Actually, I like a new term that I revised, is the throwout energy of the battery. What do you think? because my point is because for the life cycle, for the second life applications, because
Yeah.
uh, 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 I want to share this proposal to unify the functional unit in these projects and the color path in throughout energy, considering the efficiencies of the not the storage energy and the batteries. Consider the efficiencies. What do you think?
I think, yeah. All the functional units that you mentioned have their own basis, and I think they're all valid in a way. But basically, what we studied as well in MARBELL is that, yes, the battery at the beginning, we are aiming to know what the impact is within the electric vehicle context. So even though it has a second life at the end, or we wish for this battery to have a second life at the end, at the beginning, the goal is to know what is the impact within the electric vehicle context. So at the end, it makes sense to consider the kilometer as the functional unit for an electric vehicle. But if we consider this, we may not be considering, as you say, the efficiency, or correctly considering the efficiency of the battery when we do improvements in the configuration of the battery pack, for example, for MARBELL. So that's why even though it makes sense for communication, because the goal is to make a better electric vehicle in the future, and to communicate this to everybody, it would make sense to say it in these terms. At the end, for us to evaluate the performance of the MARBELL battery, it would make sense to consider exactly this, what you said at the end, like the throwout energy, or whatever it's called, like the energy that is efficiently provided to the vehicle at the end, considering the thermal management system, the whole system.
Yeah, that's a good point. It depends because it's linked to the goal of the life cycle study as well.
Yeah, but actually they're both linked to the goals of the study, because we are talking about the electric vehicle context still. So
Yeah, that's right.
yeah.
So I'm gonna jump in here just to add a side comment regarding the kilometer. So of course we're coming to the electric vehicle, but the kilometer or per kilometer, I think it's yeah, I'm gonna say dangerous, because you would be including the efficiency of the engine, for example. So or whatever, any inefficiencies or problems or advantages gained through something that it's not the battery. And yeah, in terms of the capacity and so on, yeah, again, it's a bit of a difficult question to evaluate how much the capacity of the battery represents the improvements you've done in the battery. But anyways, and maybe I think we've talked about this a bit in other situations, but yeah, it looks like the throughout or the energy delivered or the way you want to call it, it's, for me it was the best option. And then and this so the European regulation has established already what is the functional unit to go for, and I will read it. So the functional unit is defined as 1 kilowatt hour of the total energy provided by the battery system over the battery service life. So I guess this is pretty much the throughout concept that you guys have been proposing. Again, this was for a regulation that still hasn't properly defined second life, so I don't really know how this is going to come. But for the calculations we've been doing, we just consider the same functional unit, so 1 kilowatt hour provided by the battery instead to the vehicle. We just whatever to the housing system or something. And we felt like it worked. It worked in terms of reflecting the adequacy of the battery and the benefits of the second life or the problems of the second life. So I guess that we can believe that the European Union is going to push this route for the batteries in the future as well.
Yeah, I totally agree. Like this is I think we agree all of us in this. But I think it would be very important for us to section the results on because we won't have the same efficiency from the battery when it's the first life and the second life. And then we would want to know how much like how much efficiency we get from the different options of second life. Because the first one we have it clear, it's an electric vehicle, but the second one has like a variety of options. Which one would be the best for which kind of battery? Because at the end, you have a battery that could be ending in a very functional one or a very poor efficiency battery for the second life. So yeah, it would be important that like to have it sectioned and identify this.
Yeah, yeah, you're right, Violeta. Because in terms of the dimension, in the functional unit, I am energy, kilowatt hours. Yes, we can maybe unify everything, but we have different characteristics, performance of the battery in the first life and the second life. Sometimes it is difficult to reflect in this functional unit. This is characteristic.
Yeah.
Well,
Also,
mhm,
just a punctuation from what Violeta said, and just to so some of the repurposing they even merge different batteries, so that would be an added complication to this. So I'm not saying it's the straightforward solution. I'm just saying maybe we should believe in that this is what the regulation is going to bring to us, not maybe so, and then work around this proposition because uh, again, Second Life it's just complete different game, right? So
yeah, that is right. Well, I don't know if I don't have more questions. I don't know if there is question for the panels. I think we can close the the webinar. Is only to say in terms of the the grow up that we add addresses in this webinar the different challenges of incorporating the circular economy indicators into the life cycle impact assessment categories. We address the importance of the iterative LCA processes in technology development and the difficulties and addressing critical raw material scarcity within the LCA models. Also, this is main challenges. There are a lot of other ones, but this is challenges I'll be addressing in Colapath LCA subcluster. For this project, we expect to provide a good roadmap for more unified methodology for the life cycle assessment in this value chain of the batteries and new technologies. Yeah, this is all from my side. I don't know, Thomas, if you want to add something. Thank you very much for all.